So now we're going to look at electron configurations and orbital box diagrams, which you should have learned about in first year chemistry, even if you don't remember it. So electron configurations describe where the electrons are located within an atom. And there are two ways to do these electron configurations. One is to do this spdf notation, where the first number represents the n number. So this would be the n equals 1. The letter represents the sublevel or subshell. Remember, L equals 0 is an S, L equals 1 is a P, L equals 2 is a D, L equals 3 is F. And then the superscript tells me how many electrons are in that particular sublevel. The other way to look at electron configurations is to look at an orbital box diagram. The difference between just the electron configuration and the orbital box diagram is in the orbital box diagram, we represent each individual electron as an arrow. So if you remember, there are 4 quantum numbers. So this particular arrow representing an electron is in the first principal energy level, in an S sublevel, so L equals 0, 1 orbital, so M sub L equals 0, and since that's pointing up, we'll call that plus 1/2. And then this other electron would be 1, 0, 0, minus 1/2. Same thing with 2, except now we'd have 2. When we get to 2 p's, each of these would have a 2 as the first quantum number, a 1 because it's a p sublevel, and then each box represents one of the m sub l numbers. So this might be m sub l of -1. It's pointing up, so plus 1/2. So orbital box diagrams represent each individual electron, whereas electron configurations stop pretty much at the sublevels, one s, p, d, or f. Okay. When we write electron configurations, there are several rules that we need to keep in mind. The Aufbau principle, which states that electrons occupy the lowest available energy level. So we fill from lowest energy level up. The Pauli exclusion principle that says 2 electrons per orbital and they have to have opposite spins. So that's one way to state the Pauli exclusion principle. The other way to state it is that no 2 electrons in the same atom may have all 4 quantum numbers alike, as we talked about earlier. Okay, so of a group of orbitals of identical energy, electrons enter empty orbitals whenever possible. Hund's rule. So Hund's rule is why we put these 3 in individual orbitals instead of pairing this up, putting one here, and leaving that one empty. That would be Hund's rule, also known as the bus seat principle, because if you get on a bus full of a bunch of people you don't know, you'll sit in an empty seat before you sit next to someone that you don't know. And then, I just mentioned this, electrons and half-filled orbitals also have parallel spins, which means if they're by themselves, they all spin in the same direction. Typically, we show them as being up, but in this diagram, if we could have all 3 of those pointing down, and that would be valid as well. Okay. So when we start looking at the Aufbau principle, filling the lowest energy level first, when we're in a hydrogen atom, this is what happens with levels and sublevels. You can see 2s, 2p, same energy. 3s, 3p, 3d, same energy. So we would just start filling across like that. However, what happens is, as we start putting electrons into their individual little orbitals, that affects the energy, the amount of energy of all the orbitals in the atom. So what happens is we start getting these things splitting apart. And so if you remember from first year chemistry, once we get past 3p, we don't go to 3d, we go to 4s first, because the 4s really should be probably right about there and not there. So we go 3p, 4s, 3d, 4p. So after we get past the first 3 rows, we can't just go sp, d, f. And that's because the electrons, by filling the orbitals, affect the energy of the other orbitals, even the ones that are empty. So when we go to write electron configurations, we need to know the order of filling. So the easiest thing to do is to use the periodic table to figure out what the electron configuration is. Remember, S block, P block, D block, F block. So if I have this element right here, which is 1, 2, 3, 4, 5. So we have this element right here. Can't really read it off the periodic table right now. If I want to know what the electron configuration for that element is, I would start up here, 1s2, because there are 2 electrons in the s sublevel, 2s2, 2p, and then each column represents another electron going into the p sublevel up to 6 electrons. So 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then 4d, 1, 2, 3, 4, 5. So that electron configuration for that element would look like this. Now, a couple of things you'll notice is that the row number, if I number the rows, that corresponds to the principal energy level of the S and the P sublevel. So 5S, 5P, and row 5. The D sublevel is always the one number lower. So if I'm filling the 5S, then I'm filling the 4D. If I'm filling the 4S, then I fill the 3D. So I go down 1. And then down here we have our Fs, the intertransition metals, which again, those plug in down here. And it actually goes S, F, D, P, and actually it isn't even that straightforward because it goes S, F, D, F, D, F, D, F, P. So we're not really going to worry about what's happening down here. But you need to be able to write an electron configuration, and the quickest way to do that is to use the periodic table. Okay. And you'll notice that last electron configuration, it started to get a little long. So we can shorten up how much we have to write by using something called the noble gas configuration. So what we do is we look at what row the element is in. So lithium is in row 2. So what happens is we take everything that is before row 2, and that electron configuration is the same as that of helium. So helium is the noble gas, and you notice the noble gas is always in group 18 at the end of the row. So we put helium in brackets 2s1 because lithium is the first element in row 3. Ti, titanium, in row 4, element 22. So since it's in row 4, what we're going to do is write the electron configuration from 4s2 onward, which is just this right here. This electron configuration is the same as argon. So we call that, so instead of writing all of this out, we just put square brackets argon and call it done. And that's a much quicker way to write out electron configurations. So let's take a look at a couple of examples. So we're going to write the electron configuration for sulfur using both the spdf notation and an orbital diagram. So sulfur is element number 16. It's in row 3, and it's in group 16. It has 16 electrons. So we start by filling up 1s2, and that tells me there are 2 electrons and 1 s. So now I have placed 2 of the 16 electrons in sublevels. Then I go 2s2. That's 4 electrons total placed out of 16. 2p6. That's 10 electrons placed out of 16. So if I've stopped right now, you notice 1s2, 2s2, 2p6 is the electron configuration of neon. I'm at the end of row 2. I start row 3. 3s2. That gets me to magnesium. So now 12 electrons of the 16 have been placed. So the next sublevel to fill is 3p, and it would get 4 electrons. So this would be the electron configuration of sulfur. So when you go to write orbital box diagrams, in books you'll typically see every single one of these orbitals represented. For me, all you need to do is represent the outermost sp and d, if there are any, electrons. So in this class, all you need to do, if I ask you to draw the orbital box diagram, you're just going to draw the orbital box diagram for this part of it right here. So the orbital box diagram for sulfur, and the other thing is I always use lines instead of boxes. It just ends up being a little neater for the way I write. So I have a 3s sublevel, and s's only have one orbital because m sub l equal to 0. 3p have 3 orbitals because m sub l could be -1, 0, or +1. There are 2 electrons in the 3s, so I use half arrows. Again, it's a little bit quicker and a little bit neater when you're writing a whole bunch of them. When I go to fill the 3p, there are 4 electrons that go here. There are 3 orbitals, which means I have 2 electrons paired up and then 2 lone electrons. Hund's rule, these 2 guys are not going to pair up and leave an empty orbital. They're going to separate out. Since they are unpaired, they're going to point in the same direction. So that would be the electron configuration and orbital box diagram for sulfur. I'm going to write the ground state configuration for strontium in the spdf notation and the noble gas configuration. Strontium is atomic number 38. It's in row 5, group 2. So the full spdf notation for strontium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. If I add up all those superscripts, that adds up to 38. I use the periodic table. If you want to stop this and just look at the periodic table and figure out how the s's and the p's fall. Each group represents the addition of 1 more electron into that particular sublevel. That is why there are 6 groups in the p block, because there are 6 electrons total that can go in the p sublevel. There are 10 groups in the d block because there are 10 electrons that can go in a d sublevel. Now again, to save some time, to write the noble gas configuration, I look, the highest principal energy level occupied is 5. So that means everything before 5 is going to be shown or represented by the noble gas that is at the end of period 4. The noble gas at the end of period 4 is krypton. So I put that in square brackets. So this takes the place of all of that, and I write 5s2. And that is the noble gas configuration for krypton.